She is currently an assistant professor of statistics in the Department of Mathematical Sciences at Montana State. So thank you for coming.
All right, so I'll turn on the thing and then switch to presentation. There we go. All right. It's unmuted, right? We're good to go. Thank you. All right, well, thank you very much for having me. It's always fun to come to a place like San Diego in the middle of winter in Montana. They got a lot of snow last night. So I thought today I'd talk a little bit about my work in epidemic modeling, optimizing HIV prevention programs using that modeling. And let's see here. So I am guessing I don't have to tell anybody in this room that HIV is a big problem. But just for some context, these are two figures from the global report from UNAIDS in 2018, showing the history from 1990 of annual estimated deaths, AIDS-related deaths, and new infections. And these little dots here are where they were hoping we'd be by 2020. So as you can see, particularly when we're talking new infections, there's some room for improvement, although it's 2020 now, so I guess we're either there or we're not. And so this is sort of where I think some of this modeling really comes into play as a useful tool, is figuring out how to move that needle without having to invest quite the vast amounts of time and resources that you would need if you were just going to run a whole bunch of clinical trials of different things in different populations. And one of the reasons this is so important is the diversity in epidemics. So this is, again, a figure from UNAIDS. Just big picture, it's plotting out the risk groups by region for HIV infection. And without digging too much into the details, just visually you can see how much variability there is even at the regional level in terms of who's most at risk. If we start taking that down to smaller levels, we get even more variability in terms of who's at risk, what interventions might be useful, and whatnot. So fortunately, we have some things that work. You can see my more biomedical bias in terms of the things that occur to me off the top of my head. But my emphasis here isn't on listing out all those things, just, they exist. For me, the question is, how do we align prevention with risk? So put together that diversity in epidemics with this toolkit that we have of different interventions. And there's a lot of questions that I think epidemic modeling is really poised to answer well, or at least approximately answer well. So big question, how do we put together a prevention package for a particular population and risk profile? And then some sort of more, what's the word that I want? Specific questions, I guess, that can come up. So we have an intervention that looks like it works in one population. Do we think it's going to work in another population? Is that mechanism still present? What are the pressure points for intervention? So where are we missing something? Where are infections arising that we might want to focus an intervention? We have something new that looks like it is effective at the individual level. How does that play out at a population level? If we invest a lot of resources, are we going to have a real public health impact on a broader scale? And these are all questions that we can address fairly efficiently with something like an epidemic model, right? So rather than going out and doing, say, a full clinical trial of this intervention in a population, we can have this synthetic laboratory, in a sense, in an epidemic model where we can test things out and get an idea, at least of sort of the region of the space that we want to be exploring with these more resource-intensive approaches. Now, I'm not going to guarantee you that I do an epidemic model and it perfectly identifies exactly what should be done, right? It's still an approximation, but it's a good enough approximation that we ought to be able to rule out some things at the very least, and really zoom in. Yes. So, still thinking big picture, epidemic models fall into generally two broad classes. The first is deterministic compartmental models, where we are mapping out the flows of the population through different compartments. And essentially what our outcome there is what percent of our population is in each compartment at a given time, right? And these compartments could be determined by risk group, demographic factors, stage of infection, treatment status, any number of things. But as I'll point out, they get exponentially more complex the more things you want to account for in your compartments. And the other broad class is an agent-based model, where rather than thinking about portions of a population, we're actually tracking individual outcomes over the course of the simulation. I specifically work in a subclass of agent-based models, which are network models, where not only do we track each individual person's progress in our simulation, we also track relationships over the course of the simulation. So people can be in consistent partnerships over time, which does change the risk structure as compared to, say, one of these models that sort of assumes anybody can contact anybody else at any moment in time with potentially a very small probability, but some probability. So I think that this approach is much better suited for things like sexually transmitted infections than the deterministic model. People have made huge strides up here in figuring out ways to make it more flexible and account for some of this consistency, I guess, in relationships. So I don't want to just like throw it out the window, but there are reasons why I do this. And essentially, there's pretty good evidence, largely simulation-based, but evidence nonetheless that the network structure changes the path or the trajectory of an epidemic, especially in cases where transmission happens through very close contact. So if we're talking about something like the flu, where any of us could infect anybody in this room today, it doesn't matter so much the structure of people's connections because there's so many of them and they're so dense, and we're approximating that anybody can contact anybody system anyway. But if we're in a situation where people have, you know, a small number of relationships through which this pathogen can pass, suddenly there's a lot of structure in that network, and that becomes really important for understanding how this pathogen moves through a population. The other thing that's nice that we'll see as we go along is once you get past the initial hurdle, which admittedly is higher than a deterministic model, adding complexity is relatively straightforward. So we don't have this exponential growth in the complexity of our model, which is more things that we want to include in it, like we do with a compartmental model. On the downside, everything has a downside. It's very computationally intensive. So those deterministic compartmental models, you can write out a set of partial differential equations, and those are, I'm not going to say easy to solve numerically, but quick to solve numerically. People have developed algorithms for doing that. Whereas any agent-based model, and perhaps network models in particular, require a lot more computation to get to the end. So it restricts our ability to, say, explore an infinite number of combinations of potential inputs because it's going to take a fair bit of time to run each simulation. It's getting better, definitely getting better. The papers that I'm talking about today, to run one simulation, one set of parameters, took 10 days. Now I think I could do that same thing in a couple of hours. Like, it has gotten a lot better, but it still does restrict our flexibility. And the initial model construction, I think, is a bit more complex because we have to worry about things like converging to the right levels of prevalence and incidence and things like that that take a little tweaking. But here to follow up on this idea that network structure influences epidemic spread, this is the one thing that I'm going to show you that isn't something that I wrote or presented, just because I think they did a lovely job. This is from a Journal of the World Society paper by Keeling and Eames. So here we have 5 different sort of classes of network structures, all of which people have used to model epidemics, most of which don't make sense in this particular context, but it gives you an idea. So we have a totally random network, a lattice. The number of epidemic models I've seen run on a lattice sort of perplexes me because no population is structured like this. A small world network where most people are connected to their neighbors, but every once in a while you get someone who has a connection on the other side of the world or whatever. This one is structured within space, so you're more likely to be connected to people near you. Reasonable. And then this is a scale-free network, which is a different sort of degree distribution. You have a few really highly active nodes or agents and a lot of not so much that are connected to those people. And then what they did is they just simulated a very simple epidemic over this. So this is nowhere near like HIV level complexity, but you can see that for those 5 different structures, we get very different epidemic patterns, right? What's the peak? This is the percent of the population that's infectious at any given time, right? So in that totally random network, by the way, in all of these people have, on average, 4 connections, right? So it's not like one has just a lot more paths to go down than another. We get just immediate through the roof, and then it trails off. Ones with more structure tends to be slower, so you have perhaps a little more time to intervene, for instance, before you hit that peak. Down here with the spatial and the scale free, we just we get still near to the beginning, but a little bit later. And so this is essentially the type of thing that we're trying to account for by using network models. The fact that this kind of structure really does make a difference. And it's beyond just, well, what type of a network do we have? So this is an example looking at really small changes in the numbers of connections people have. So in all of these, we're going from 44 down to 32% that have just one connection, and from 56 up to 68 that have either 2 or 3. So our mean degree ranges from like 1.4 to 1.7 or something. Like on average, people have less than 2 partners in all of these cases. And what happens is the network becomes so much more tightly interconnected. So down here, we have tiny little groups of people that are connected in these sort of stringy trees, whereas up here, we've crossed a threshold, and now all of a sudden, this is 64% of the population in this that is connected to each other through some path in here. And that is, you can think of as a measure of our epidemic potential. You put one infection into one of these networks. Down here, it's not going to go anywhere. It can't. Up there, we're doomed. And this is with fairly low degree, low activity, right? Nobody here is the super spreader that was a popular hypothesis for a while there. There's just a whole lot of people that get connected through their neighbors. The other thing that the network model in particular can capture is timing of partnerships, right? So if we think about, like, I don't know, this little branch here, if this is, say, aggregated over 6 months or something, how many partnerships people have had. Whether this person gets infected before or after they take up with whoever's on the other end of that edge really matters for all these people down here, because if it's after that relationship is over, it can't get to them, even though they are, in theory, connected through this network. So that's why this idea of relationships matters so much, because both risk is sort of contained within a partnership for some period of time, and the sequencing of partnerships can have a real impact on the risk of others further out in the network. I still don't have to walk over there to do that. I mentioned complexity. So this is something that I put together to visualize what goes on sort of in one of these models. So this is the basic outline of how one of these simulations goes. So we have a population, it ages, people enter it, people leave it, that kind of stuff. We update the contact network. In my world, that's typically a sexual network. Partnerships end, begin, short-term contacts happen. We see, is anybody eligible for an intervention? Deploy interventions, and then we see in what cases does transmission pass over a link in this network. T+1, we do it all here. But what happens is that any of these bins can influence elements, features of the agents that can then influence what happens in the bins in the next round. So, simple case, population dynamics, aging and entrance to the population affects who you can be connected to in the next round of the network. If an intervention, say, changes someone's behavior, that then affects who can transmit later on if they become more adherent to treatment or something of that nature. So there's this huge amount of interconnection where this complexity then allows us to see patterns that we absolutely would not see if we just looked at rates of things in different populations, because so many things affect so many other things. But once we have this structure going, if I say, well, actually, I think I have another intervention that's going to change variable load in a different way, no problem. Change that really quickly. But getting here takes a bit of doing. So why the focus on complexity? Customizing something for a population requires complexity. If we're going to come up with something that's really targeted at a particular situation, we need to know a lot about that situation. So this is most of, if I cut off, one table and a supplemental appendix in the paper that I'm going to talk to you about in a minute, which has parameters that we estimated from a whole bunch of different data sources for 2 different populations that go into this model. And some of these boxes are multiple parameters, for instance, down here. So that's a lot already. There's 2 more tables that I didn't put on the slide. And so there's a lot going on here. And I think that's the next one after that. So this is coming from this paper. So I'm going to talk about the way we've addressed some of these questions that I presented right up in the beginning in the setting of the Bohme project. Prevention umbrella for MSM in the Americas. So it was an MP3, if any of you are familiar with that mechanism, a while ago now, where the point of the funding was to use epidemic modeling to design potentially combination prevention programs. And so this was our base paper. I mentioned that there's a large startup. This is just, let's get something that actually looks like it approximates reality in some way and see what it tells us. So that's understanding our population. And so that table was the first set of, or one set of parameters from that. And so we had data from essentially urban MSM in the US, and then most of the data, initially it was supposed to be the Americas, but basically everything from South America came from Peru, so we decided, truth in advertising, to just call it Peruvian and not North and South American. So this is a listing of all of the things that we kept track of in terms of this model. So we have something like 16 attributes on each of them in our model. These are all probabilities governing disclosure and diagnosis and how long partnerships last and when does unprotected intercourse happen. And then over here we have changes that can happen to each man at each time step. If this were a compartmental model and we have, say, just 2 levels for each of these things, right? That's 2 to the 16 compartments that we're trying to use to characterize a population. And, you know, some of these are only relevant for people who are infected. There's some nesting. But we didn't say dichotomize everything either. So we actually have a measure of viral load. And we had a continuous function that relates viral load to probability of transmission, for instance. So we get a lot more nuance, potentially, than you would from a comparable compartmental model. All right, so once we got estimates of the distributions of all of these things and the populations of interest and all of these probabilities, and we ran it all forward and saw that, yes, in fact, this does end up with something that recreates what we think is the prevalence and incidence in these populations and subpopulations thereof. Then we get, these were the primary results. So I said we're understanding the population here. So mainly what we were looking at is where are infections coming from? So this is that pressure point question. This is a little tricky to read because we have 2 competing models for how viral load relates to probability of transmission. And then within each of those, we have the US model and the Peru model. But for instance, I think one of the things that got a lot of attention at the time was up here, looking at the contributions of acute versus chronic infection. And I don't want to downplay acute infection relative to the percent of infected men who are in the acute stage. This is still very large, right? It's much higher risk per person. But if we're talking ending the epidemic, right, even in the worst case scenario, we're going to have to pay attention to transmissions from the chronically infected but unsuppressed, right? Because that's still 40% of transmissions. Similarly, and this is probably not surprising at all points in the treatment cascade, there are weaknesses that would need to be addressed, right? And they're all contributing comparably, perhaps, to burden of disease. And then the other one that we looked at, because this was one of the first models that I know of that really separated out main partnerships versus casual relationships, is where are transmissions coming from in that regard. Right? And so we have something like 30–35% coming from main partnerships, which are series coordinates. So that's, again, a place that, well, are there interventions that would specifically target that situation, which is a bit different than thinking about how do we manage people's risk from casual UAI. By the way, feel free to interrupt me with questions at any time.
So in the model, do you assume anything about use any parameters, assume anything about the network structure? Like with ERCMs, you look at triads or 5-star?
Yeah, so we assume, we put in what we can measure. So we have degree distributions about, momentary, how many main partnerships do people have, how frequently are there these casual contacts happening, and age mixing, so tendency for contacts to happen based on the distance between the ages. And in the US, we also had mixing by race, which creates some of that higher level structure in there, but we can't, for instance, measure clustering or triadic closure, things like that. So we don't put it in, so it's constrained only insofar as the other things that we know constrain it.
Okay. Thanks.
So probably when you looked at that massive list of parameters, you said, well, you can't possibly have gotten all of those right. What happens if you're wrong? Which you should absolutely be asking. That's a very important question. And what we do is we do sensitivity analysis. So this is an example of the things that we tried. This is one place where the computational issues do come into play. We have to be selective about what we do sensitivity analyses on, because we can't say, well, we're just going to vary everything across the plausible range and all the possible combinations of all the plausible things, because we don't have the computational time to get that done. So in this case, we're looking at, in terms of the role of main partnerships, percent of transmissions occurring within, what happens if we're wrong about how long these partnerships last. Right? So this is what we reported. If they're actually half as long as we thought versus half again as long as we put in, how much does that change that contribution? And in this case, it's not a whole heck of a lot, right? They're still basically the same ballpark. Over here, it's a little bit more of a story. So we're looking at the interval between tests. If we underestimated how long people go between getting HIV tests, right? How does that change transmissions from those who are diagnosed relative to undiagnosed? And unsurprisingly, the longer people wait between tests, the more of them manage to transmit before they are diagnosed. So that's perhaps not surprising, but certainly a definite implication in terms of where one focuses one's energies, depending on where on this scale you think we really are. And so providing stuff like this allows people to come back and say, how are you way optimistic, right? It's got to be at least 3 times that long. You can see, oh, okay, well, now that changes the picture. All right, so that was understanding our population. The next question that we tackled is testing a proven intervention in a new context. So this is looking at male circumcision in epidemics with men who have sex with men. And there was very strong evidence for protective effect of MMC in heterosexual epidemics, right? 2 out of 3 major trials that, and maybe more, 3 than I stopped early for efficacy. So like that's not a thing that happens very often in clinical trials. That means that it was so good that they actually couldn't ethically keep going. They had to just start giving intervention, right? And estimated across the 3 of them pretty consistently something like a 60% reduction in risk for the men or circumcised. But then there was the question, these are all in heterosexual epidemics, how would this translate to epidemics in medicine? Right, so the mechanisms of transmission are a little bit different. And so we decided to tackle that question. And this is where having put together a network model becomes really nice. So we had our base model, everything's lovely, we kind of know what's going on, and we said, all right, we're going to look at the impact of circumcision. And this is what we did. We had to add 1 attribute to individuals, which was essentially their probability of uptake. And then when they enter the population, we flip that coin and label them yes or no. And then what is the reduction in the transmission probability associated with having been circumcised? So that's just adjusted 1 model level parameter. In our transmission module, we had a times P for those where they've been circumcised. And that was it. So now we have a pretty quick, moving on to the next intervention. And this is our main result. So over here we have 25% uptake. Over here we have 50. This model, by the way, was done just in the Peruvian setting because coverage of MMC was basically nil. So it was sort of the best case scenario of where an impact could be had. And you can see that well, there's a lot of variability, but overall, it makes a difference, but it doesn't make a big difference. So over here at 25% uptake, we're looking at something about 5% reduction in incidence overall. Not 5 percentage points, 5%, right? So it's not nothing, but it's not a whole heck of a lot. Over here, if we get up to 50% uptake, we get up to something like a 10% reduction. Things don't always work out that nice and linear in these kinds of models, but in this case they did. And we can look at it from sort of a cost perspective, which is here the cases averted per circumcision, or if we inverted the number of procedures that need to happen to prevent one transmission. And we're looking at cumulatively out to 25 years, roughly 10. 25 years is a really long window. A lot changes in 25 years. I'd probably look more like 10 years or even 5 years. And there we're looking at 10 to 20 procedures per infection averted. And it's actually not all that different for the 50% uptake, which suggests that there's not tremendous downstream effects percolating through the network, which I suppose isn't surprising since the impact overall was relatively small. So I've never done actual cost effectiveness analyses, but these are the sorts of things that, like, all right, we'll give the information that one would need to make that decision. I don't know how much the procedure costs, but I can tell you how many you might need to do to achieve your goal, and then you can make that decision, right? So that's high-ish, I don't know. And then the other wrinkle that we looked at is so far, this is all assuming that men have a role. They are receptive, insertive, or some of each, and they stay that way. If we allow them to switch, which seems like a reasonable thing, basically goes away. So now we have, if the average time to role switching is something like 3 years, we have no effect. If it's 5, maybe we're seeing something out towards the 15-year mark, but statistically speaking, I couldn't either of those say to you, it looks like there's something going on there. So this one was an example of narrowing field, right? Based on what we're seeing here, probably not where you want to put your money if you have limited resources. Not that it doesn't do anything, and not that it shouldn't be available, but if you're going to be investing in large campaigns, maybe we're looking at something else being a little bit more efficient in making impact. All right. Next up, targeting a new intervention at the population level. So this is looking at PrEP, same setting. And so at the time we were doing this, they were just getting to the end of some of the first big PrEP studies. So this is a New York Times article about the IPREX results. All of these studies were occurring about that time, and they're in a lot of different populations. And so we do have, right, evidence within our population of interest, heterosexual men, and in others. And so then the question is, okay, this looks like it works at an individual level. What's going to happen if we manage to scale this up? How do we do this in a way that maximizes the impact? So again, our modifications are fairly minimal. We have to add a couple of attributes. First of all, would they even be willing to try? And secondly, how well do they adhere? So we had 3 levels of adherence, basically. One that's equivalent to, yeah, all right, once then I stopped. One that's like a couple of doses a week, and one that's full adherence. And then reduction in transmission probability based on level of adherence. And then as a sort of sensitivity analysis, we looked at risk compensation. So the idea was that people have a sort of level of risk they're willing to accept, and if you help them reduce that risk, they find ways of increasing it to compensate. So the big question was, are people going to feel invincible and undo all of the benefits, right? here we're really looking at targeting strategies. So this one up here is essentially a general population study. Anybody who ever engaged in unprotected receptive anal intercourse was eligible. And then we get more and more restrictive. So we looked at targeting based on main partnership status. Okay. So if you're in a discordant partnership, maybe the negative partner should be getting on PrEP. And then we looked at targeting based on levels of casual activity. So we have the top quintile, which in our model is roughly 1 casual contact a week, give or take. And then the top 2, which ranges from about 1, so the second quintile averages about 1 casual contact a month. And then combinations thereof. So this is main partnerships with the top 5th, main partnerships with the top 40%. And what we can see is basically the more people who are eligible, the more your reduction in incidence. This is hardly surprising. And the reductions are non-trivial. So this is the sort of combined measure of uptake and adherence, which is sort of an effective percentage coverage in the population. And at relatively moderate levels, I guess, 10, 20%, we're seeing 10 to 15% reduction in overall incidence. If you can get it up to 35, now all of a sudden it could be quite substantial. And then over here, we're looking at that cost thing again. So this is person years on PrEP per infection averted. And what you'll see is that we're most efficient when we target that very high activity group. This is not surprising. We get about 12 person years on PrEP per infection averted. The main partnerships, it's something like 15-ish. Once we expand to the top 40%, we're getting down to like 23. And if we're targeting everybody, it takes like 35 person years, right? So it's true, you maximize your impact by giving it to everybody, but there's a lot of people taking pills they don't need, right? Which reduces your efficiency. So again, the trade-off, I don't make a call, I just provide the information. And if you combine, say, that top quintile and the main partners, you stay relatively similar person years, right? Right, and then the question of risk compensation. So here we are looking at percent increase in casual UAI and percent increase in UAI and main partnerships. This is a very large range. So we go from, this corner is model as is, and then we go up to quadrupling the frequency in both directions. And our contours are the estimated reduction in incidence in this particular, I think this was the top quartile targeting. So this is a 20% reduction, 10%, no change, actually a 5% increase. And then the shading is sort of our strength of evidence. So basically we have pretty strong evidence that regardless of how much main partnership activity increases, we can up to 150% increase, so between double and triple, casual activity, and still maintain something like a 10% increase in incidence. That's in the US. Peru, it was a lot more sensitive, but this is still up to a 50% increase in casual activity, which is actually quite a large increase. This may have been overkill. We're still looking at probably something like a 10% decrease. All right. Where are we at in time? 2:40. All right. So that's the stuff that's actually I've done. Where I'm going from here is thinking about expanding to multi-layer network models. So everything I've talked about so far, we're modeling a contact network, we're modeling transmission over that network, we're changing structure, how the transmission happens, all that, but it's all here in this layer. What we're looking at doing is expanding to include other types of networks that then could co-evolve over the course of the simulation. So for instance, phylogenetic linkage, Susan about that this week, right? We have the same actors in the network, same nodes, but the edges are now determined by something different. In this case, the connection between the two is relatively easy to define, right? When a transmission happens down here, we have an edge up here, and then a little fudging around that for relatively closely connected nodes. Once we start getting up into, say, social network and geospatial, how those are connected to either of these is certainly an open area. I know some of you are working on this. I would love to hear your thoughts. But the idea here is, I hope I've convinced you that network structure matters. And so it matters for these simulations in terms of giving a picture of how things work, but perhaps we could also leverage it in the real world, either as part of an intervention or in a trial. And here I could go into a big, long thing about spillover and interference in causal things, which I won't. But basic idea is, if we have clusters down here, a trial would be more efficient if we could effectively randomize those clusters to the same intervention, as opposed to, well, these two end up in opposite arms, but they're affecting each other. So if there are benefits to one, they can pass on to the next, right? So the hope here is to get tools where we can essentially simulate the design of such trials and get an idea of effectiveness, power, whether we could use something like a social network as a proxy for a connection in the sexual network, yay or nay. Not really the model that decides that, the inputs decide that to get from somewhere else, but if that turns out to be something that seems feasible, then, well, what happens if they're close but they're not exactly the same? We pursue this kind of strategy. And then, of course, lots of people have funded this over the years. I think they got involved. Any questions?
So I know we've discussed this before, but on the last slide, one of the challenges we've had when we've talked about the multi-layer network is things like the social network can change dramatically over the course of a study.
Yep.
How would you control for that? In other words, clusters within the social network could reassociate from one arm to the other and back.
So is the question how we make that happen in a model, or how we think about a design in a situation where that can happen?
The latter.
Ideally, now I'm my puzzling, if we had an idea of how often that happens, right, then we can probably pull over some of the stuff like Victor and I worked on with spillover in cluster randomized trials of prevention interventions in infectious disease that might allow us to at least start to account for that without having some idea. It could be like sensitivity analysis where we say, well, how often does this happen?
Yeah.
0 to 50%,
Yeah.
and how does that change our inferences?
Right.
Hopefully, I mean, it'll change it a lot.
Yeah.
Get to that much, but beyond that, I suppose, I mean, in an actual trial, right, you would know if you have some well, it's a social network cluster potentially that would be randomized to a thing. And you wouldn't necessarily know how that aligns with clusters and that. Yeah, okay. So assumption, sensitivity analysis,
Yeah.
best
Okay.
estimate, see what we can do.
So in your agent-based models, can you impose additional structure other than just the network? Like, so you have San Diego County, you have a network that's, has a degree distribution 1.7 in this zip code, different zip code, communities within your. Then you have some mixing. You need to know the mixing, right?
Yes. So yes, absolutely, you can do that. It would require more information than I work with, so I haven't tried. There are people who are like simulate Chicago, and absolutely do those kinds of things. I have never gone to that scale, but you could with the right information, absolutely do that.
Maybe you could use molecular or genetic clusters to sort of approximate that. What the spillover would be.
Yeah.
The boundaries would get hard, I think. Where are you getting your geospatial location data from? I'm just curious. It's been a really difficult thing.
So as soon as I've gotten thinking about that is something like zip codes or something, like a very coarse approximation, especially as we're thinking about if this is the network on which randomization is done. It has to be a fairly dirty kind of measurement, not like how much time do you spend in this 4-block area or something like that.
Okay.
Yeah,
It's really hard. Yeah,
for sure.
Thank you.
So you're not a big fan of this.
Lattice.
Oh.